Okay, the second title is evenly spaced downsampling, as known as pooling, guys. Well, it might sound a bit weird to you that I call pooling layer kind of co-design layer, kind of co-design approach, but actually it is. Because, you know, in our networks we make pooling, which downsamples the activation's spatial dimensions. Very good, okay. But we don't have to. I mean, imagine you have an artificial neural network where you connect everything to everything. Well, that would have been much heavyweight, but it will have the necessary connections. By doing pooling, actually, we are lowering the number of multiplications as well. So actually, pooling was one of the very first co-design approaches. MaxPool is one of the very nice examples. I've just taken the figure from here. So just try to find the nice links that I provide, because in these links there are very basic explanations. If you forgot anything about something that I'm trying to teach you on that slide, those links will provide you the necessary background to catch up. So never miss those, guys. This is a page from Google, so it's just very fundamental. You can find it yourself on the internet as well, but just know that the links are very valuable as well. Whatever. So guys, you might think that pooling is not a co-design, it's something natural, but it is not. Because when you first learn deep learning, if not from my own course, it shouldn't have been much longer. I mean, for a couple of years you have known deep learning, and when you first learned deep learning, there was the pooling layer, because pooling layer is like 7 years old. However, if you go back to the history of neural networks, there was no pooling layer. The reason we had pooling layer was to make the receptive field larger, one thing, to create better features, and another thing, to make the activation size, spatial dimension size, smaller, so that we'll make lesser multiplications. So these were the baby steps. Then these baby steps grew, and we've started to take more mature and adult steps, like channel reduction. Channel reduction is actually using 1 times 1 convolution. You remember what was 1 times 1 convolution? Because in week 3 or 4 we have seen different types of convolutions, because different types of convolutions are like the history of the co-design techniques, because co-design evolved by finding specific convolutional layers like 1 times 1 convolution, or grouped convolution, which is an important title for MobileNets, actually, group convolution. Whatever, let's remember 1 times 1 convolution. If you go to the website, clearly, I've actually provided this website in week 3 or 4 when we were talking about different types of convolutional layers. Here, different types of convolutional layers, and if you remember, 1 times 1 convolution was doing nothing in the spatial domain. However, so this is the spatial dimensions, W times H. This is your activation. This is the output of the previous layer, input to this layer, the current layer. It has D channels, depth, D depth. All D depths being intertwined in all D dimensions by multiplication, and by using this you obtain one layer. With another one-to-one convolution layer, you get another layer. So you are taking a linear combination of all the weights here. With a ReLU layer, you're actually taking a non-linear combination, but that's another story. So channel reduction. What did we do was, from a depth of channels, and by combining them with some weights, we've reduced the number of channels by using a 1 times 1 convolutional layer. So 1 times 1 convolutional layer helped us to reduce the channel depth. This was also another important co-design step. At that point on, we had the chance to decrease the number of depths in our systems. Be careful. The previous step, this was to reduce the spatial dimensions. This one was to reduce the depth dimension. So these were the first steps. Then, with new architectures, just like the FCN or the UNet we've talked about, the researchers, starting with 2015, rejected to use fully connected layers, because fully connected layers are very heavy. Everything is connected to everything. They have found solutions in which they didn't need to use fully connected layers, because when you use fully connected layers, your computation and your number of weights increase crazily. You'll remember, guys, those among you who have taken the previous semester's course will remember this. Much of the calculation in LXNet or VGGD are done in the fully connected layers. Actually, we have talked about this in the first weeks of this course as well. So the second step was getting rid of the fully connected layers. So we have made the spatial dimensions smaller. We made the depth smaller. We have got rid of the fully connected layers. Good. What else next? Then, with actually Inception module version 3, it is also called Inception Module C, we have tried to factorize convolution operations. For example, instead of 3x3 operation, we applied parallel 1 times 3 and 3 times 1 operation. This was cheaper both in multiplication numbers and in latency, because these are wide operations. They are done in parallel and concatenated. So we have studied, the researchers started to study on the very nature of the convolution, trying to get everything much simpler and simpler and simpler. So Inception model, if you want to just remember Inception model, if, as far as I remember, we've covered in week 5 or 4, I don't remember, just get back to it. But factorization, so kernel reduction, making the convolution simpler, was another step which is a bit more advanced. Then the co-design continued, like in the architectural domain. In the quantization domain, they've done other things. And at this point on, people have started to work on, try to find more advanced methods to make the architectures more efficient. Actually, the title that we're going to talk about today is one of them. There are many of them, but I'm going to talk about 2 of them today, which will give you a general idea about how you can find more efficient solutions to convolutional neural networks. Okay, let's continue.